All right, hi everyone, and thank you for being here. Welcome back to the seminar series. So our speaker today is Lalitha Sankar. She's a professor in the School of Electrical, Computer, and Energy at Arizona State. She works on a lot of different things at like intersection of information data sciences. She has a background like signal processing and learning theory and control theory. She works on machine learning and like the design of machine learning algorithms. She works on fairness, on privacy, on robustness. So like lots of like different topics are relevant to us. And today she's going to be telling us about her work on imbalanced tilted scales, assuring fair performance. So Lalita, it's on you right now.
Thank you, Juba. I really appreciate you inviting me, and I'm excited to talk to this wonderful small audience. Keep asking me questions as we go through this. And a big thanks to the NSF for supporting me on all this work. All right, so this is joint work with two of my PhD students, Nathan and Monica. Monica just graduated, and Nathan is soon to graduate. And a part of the work is joint with, the first part of the work is joint with Christos Trampoulidis at UBC. Okay, so broadly, this work is about how do you train inference models to do well when you know there are imbalances across classes in your data set. Now, that's the explicit imbalance. There are also implicit imbalances that come up when there are subgroups within classes. So we'll talk about each one of these, and let's start with some examples. Cancer detection is a very classical classification problem, right? And oftentimes it's done using images, which are slides, imaging slides of specific cells in specific parts of the body. So a malignant tumor, the cells are bigger, and a benign tumor, the cells are smaller typically. All right. However, the good news is most people in the population do not have cancer, and as a result, the number of malignant tumor slides you will see are far fewer than the benign tumor slides. So you have to train a model. You want to really detect cancer sooner than later. You have to train a model because it requires fitting to a rare class. So broadly, this work is all about rare event detection, but doing it with very good accuracy. And we'll start with why state-of-the-art models don't work. Now, a broader perspective on this is these cancer imaging can be collected at two different hospitals. One is say a wealthy suburb, like, say Upper East or West Manhattan. And the other could be, say, Harlem or some other parts, maybe Queens or Brooklyn or something, or Long Island near a Superfund site. And one of the hospitals, the one which is wealthy or is in a wealthy suburb, has a pink stain, and the other one has a purple stain. So both hospitals have no cancer slides and cancer slides, but the slides with cancer in each hospital is stained in a different color. Okay, I mean, both slides, it doesn't matter whether you have cancer or not, the slides are stained differently. So now when you train a model to learn, you have to take into account not only class imbalance, what will also happen is you have to make sure this model does not learn spurious correlations. It is going to learn in each hospital that cancer cells are spuriously correlated with the stain, and this is not a good generalization methodology. And when in these hospitals just change color, or they go out to an externally sourced radiology that uses one of the two colors or a different color, it's not going to do well, the model. So how do we make these models better? The broad answer is we're going to look at assuming that we have very large models, and we're going to talk about fine-tuning these models. Okay, so let's go back to the first problem, which is combating class imbalance. The standard way of training in machine learning is what's called empirical risk minimization. So you pick a loss, that's your risk. You want to minimize this loss, and you do it empirically, meaning with the samples. You don't have any expectation. This is all an average over the samples. And suppose these blue samples are all the no cancer samples, and the red samples are the cancer samples. All right, you put the same weight on every data point. And what does this do? It actually trains for minimizing the loss, which in turn should maximize average accuracy across both classes. And when you have very few samples, you will get great accuracy for the majority class, because there's enough samples to learn from it than you will for the minority class. All right. One way people have been addressing this in the literature is by saying, hey, we have too many samples of the majority. Let's throw away some and balance it to be the same number of samples as the minority. So in this figure that you're seeing here, the light blue ones have been thrown away. And of course, you can do this many, many times by randomly sampling. So you will also have a little confidence interval about your results. Okay, so this is why you achieve balanced accuracy, but at the cost of variance in your results. Okay, yet another way of doing it is to upweight. You do not throw any data, you keep your majority, but you upweight your minority samples. And oftentimes, the very standard way, and immediately in your head, you may be thinking, oh yeah, let's upweight it proportional to the priors that are seen empirically. And so I'm upweighting it many more times. And what I'm going to tell you is that that is not fully the right answer. Okay. All right. So very simply setting up the problem, this is just saying if you had a loss L and you wanted to learn a model F, which is parameterized by theta, then you would minimize this loss. In theory, it would be over the expectation of the data set, which are the features, which are d-dimensional, and y, which is the class, right? What I've done here, compared to, unlike other places, is I've pre-multiplied the loss by a factor C that depends on the class. And let's see what that means. If you're doing classic risk minimization, that C is 1 across all the classes. If you're doing downsampling, you keep the C as 1, but you're changing the prior probability here on the classes to be uniform across all the M classes. If you're upweighting, what you're doing is you're changing the C to be, say, for example, the inverse of the prior. Okay? All right. So because there are M classes, this is 1 over M times this. Okay? All right. Because that's really, this is proportional to the number of samples. Okay. So in a prior work, what we showed was that whether you do downsampling or upweighting in this population setting, which is where you have complete access to the distribution, and you may think of that as having very, very, very large number of samples. Okay, extremely large number of samples, everything is well represented. Upweighting and downsampling are theoretically the same thing. You can sort of plug it in there, those C's, and you'll see it immediately. Voila. All right, so in theory, at the population setting, you should get the same thing. But then the question is, why not upweight all the time? There's no variance penalty from dropping the data. It's also optimal for balanced accuracy, it seems. Here is the caveat. The reason people haven't been thinking about upweighting is because there's both a little bit of theory and practice that corroborates that it has no effect in the over-parameterized regime. And what do I mean by the over-parameterized regime? This is the regime where the number of model parameters you have, D, is much larger than the number of samples you have. Think about a very, very large foundation model. You still have maybe 100,000 samples, but the foundation model is 4 billion. Okay. In those settings, because you can really fit so well to the model, to the data becomes almost separable. There is no value to weighting because the direction of the classifier doesn't change. And that's what implicit bias results also tell you. However, if you're fine-tuning with only a few parameters, where what I call is we are in the proportionally parameterized regime, D and N are comparable, can you then provably correct these large models? So we take a large model that's been pre-trained on these hospital slides. We know that these models are biased towards the majority. Before I release this model, can I fine-tune it so it'll work across all hospitals independent of the cancer populations and independent of maybe even the kinds of stains they use? Okay, so we're going to talk about fine-tuning. So in your head going forward, I'm going to talk about a very specific fine-tuning. All right, last layer retraining. So let's assume that this one big hospital or all these hospitals collaborated, put their data in the cloud, and you trained a large model. Or one big rich hospital that has access to a lot of data did this. Okay, there's still, the model is going to be biased by the data they had access to, but that's a starting point. And what we do is we freeze all the layers of this very large model. And the only thing we're going to change, because this is classification, is the last linear layer. So these yellow and purple weights are the ones we're going to change. In practice, and this was first observed by this beautiful paper by Polina Kirichenko and her advisors at NYU, that you don't even need to change a lot of these weights. A very small number of weights can allow you to get fair accuracy, whether in the class setting or across groups when you have subgroups. All right, so retraining the last layer has proven to be highly effective empirically. What we want to do is understand it theoretically. And this allows us to control the dimension D to avoid overparameterization. Okay, all right, so what the kinds of theoretical guarantees I'm going to give you in the next few slides are in the following regime. This is for theory, but it seems to work really well in practice. D over N, the ratio of D over N delta is a constant. All right, and it's between 0 and 1, but D over N are quite large, both of them. Okay, so even if you, I mean, in practice, of course, we're only doing this could be 2000. We assume that we have proportional number of samples to train. Okay, all right, so the ERM problem is one of the following. What is the weight that I put on one of the two classes? I mean, you could put a weight on each class, but if there are only two classes binary classification, it's enough to consider weight on one of the classes. I need to find this optimal weight rho such that I get very good accuracy for both classes, and the kind of accuracy I'm looking at is balanced accuracy. Okay, and I still want to learn these last layer model parameters, theta. Okay, so in this setting, the problem simplifies to a linear model, as you can see here. And the xi here is not the ambient data, it's the latent data that comes from the last layer of the frozen model before it goes to the linear layer. If anybody has any questions, you can ask me now. Okay, great. All right, so here's our most recent result. This is going to be presented at NeurIPS. Here is what we're saying. This function that we model as, so if your data is a Gaussian mixture, so you can model this latent space approximately as Gaussian mixtures, one for each class. We're looking at class, obviously for tractability reasons, you assume that one class is mu in mean and the other class is minus mu. The priors are pi plus and pi minus, and pi plus is smaller than pi minus. Okay, so pi plus is the minority class, pi minus is the majority class. The optimal weighting scheme assigns a weight of 1 to the majority and the following to the minority. Now, if you stare at it, you see this ratio pi minus over pi plus. That is intuitively obvious. It's the inverse of the priors. So I'm going to upweight my minority class rho by rho, which is proportional to, the prior for the majority divided by the prior for the minority. But that's not the only term. I have another term in here. And if you stare at this term is meaningful only when the parameterization ratio delta is between 0 and 2 pi plus. Okay, so what am I saying? If your minority has a probability 0.1 or something like that, this delta better be between 0 and 0.2. And that's the only regime where you can actually get balanced accuracy. And if you want to bring yourself down to this regime, you have to make delta small, which means you have to increase the number of samples, so you see more of the imbalanced class. Okay, so the key ideas here is because we modeled our data as Gaussian mixtures, we can actually use convex Gaussian minimax theory, and that reduces this complex optimization, D plus 1 dimensional optimization, to 5 scalars. And you're welcome to look at our paper. I have links at the very end. Okay, now then the system, these system sort of equations depend on the magnitude of the mean mu and the Moreau envelope of the loss. Okay, so I'm not going to tell you what the Moreau envelope is. It's an integral of the loss. Okay, all right. For squared loss, we can have closed form for the Moreau envelope, and all of these results are for squared loss. Okay. In also we can solve for this this result only when, I'm so sorry, when you have equal weighting for the two classes, which means you're not doing anything, you're doing classic ERM, or when you are forcing balanced accuracy. That is why the bias B of the model is 0. It passes through the origin. That's balanced accuracy. And that leads to you having a rho equals to rho star, which is this. Okay, these are the two settings where we get closed form. Let me explain what I mean by these results. So on the left-hand side, you have some pi plus, which is really 0.2. That means your data is 20% for the minority class relative to the majority, which is 80%. And your delta, you're in the last layer, and you have sufficient samples, and you have enough number of parameters that is also 0.2. So you're matched, all right? And delta is actually less than 2 pi plus, which is 0.4, right? S is the magnitude of the mean, and that's just set to 1. So the two means for the two classes are at 1 and minus. Well, they have length of 1, and they're in this hyper n-dimensional, d-dimensional space, which is centered at 1 and minus 1. Okay, so what is happening here on the y-axis? I have the class per class errors, accuracies, well, 1 minus the accuracy, which is the error, and on the x-axis, I have the weighting factor rho. Okay, so in this setting, if I weight rho sufficiently enough, so here I should weight it about inverse of 8/2. So it's about so 8/2 would be 4, but then you have to add something, and that's what brings you to this point. So this is the best point according to theory, and if you see practice, this is for really Gaussian data, you see that the two curves. So obviously, when you improve the accuracy for the minority, you're going to take a little bit of hit in accuracy for the majority, all right? But both of them improve, and the error is really small, very close to this value here. And theory predicts this line here in red, okay? However, what I'm saying is that if your number of samples are too small, so delta is larger than 0.4, you can never improve the accuracy of the minority to match that of the majority. So these two curves never meet, and that is what that result tells you. So even if you do these classical methods of inverting the priors, you are only going to be limited to these points. Okay. Questions? Okay, so now let's go. So you can ask the question, how does downsampling do in this regime? So on this curve, I have the error plots for each class. So it's in blue and red for each of the classes. And then I have a solid lines for weighted ERM, which is what we're looking at, and dashed lines for the downsampling method. Okay. Downsampling also allows you to achieve balance accuracy. But the error that you get is worse because when you downsample, you're throwing away some of your samples. As a result, you're increasing effectively the proportional parametrization ratio, delta. Okay, so when the parametrization ratio delta increases, you are less likely to be more effective in these methods. Okay, questions? Okay, so let's look at a very simple image classification application. We're looking at CFAR10, and clearly we're in the classification, binary classification setting. So I'm going to pick two classes, cats and dogs. And here's what we did. We used a backbone ResNet. That's the frozen layer. Layton dimension that the last layer is 256. And the number of samples we're using to fine tune is about 90. That's the total number of samples. So what do you see here? As you increase the weight for the minority class, you basically see that theory predicts the weight to be this red vertical line, and in practice, you get the black vertical line is what theory predicts, and the practice is close to the red line. It's very, very close to what you predict. Okay. On the other hand, if you had far fewer samples, our prediction gets worse from what we get in practice, and the errors are getting smaller, but this is an example. You get much more variance in your data, and this is an example of where this delta is getting larger and larger, and at some point these curves will not meet. Okay, so this rho star, which is our red line, I think I said it the other way, achieves more balanced accuracy when you're in the right setting of delta. Okay. Okay. Questions? All right. All right. So that was all on class imbalance. So if I had to do this in the setting, let's go back to the setting we're talking about. You have cancer data from two different groups of people: the normal group without any tumors, and the class without, which is normal slides, and the class which has tumor cells in them. Okay. However, each of these can come from either one of the hospitals or the other hospital. So that's sort of like, you're mixing data from multiple hospitals, and each of these hospitals, assume you have just two hospitals, each of these hospitals use a different stain. So hospital A is using a pink stain, hospital B is using a purple stain. Okay. And it's also possible that, if you recall properly, hospital B is near a Superfund site in America. A Superfund site is where there was a lot of pollution, maybe from oil wells before or other things, and that's more likely to induce cancer. And the other one comes from a rich suburban hospital, has fewer cancer. All right. So there's a natural imbalance across the two classes. So the normal is the larger data set in hospital A, whereas the tumor is the larger data set in hospital B, and vice versa. Okay. What we want to do here is we want to make sure that every group, irrespective of the hospital or cancer or no cancer, has the same accuracy. So now I've gone from balanced class accuracy to balanced group accuracy. Ideally, you want to optimize for the worst group. Now, that's what's called distributionally robust optimization. That's very hard to do in practice. It's computationally intense. So a little surrogate for it that people use in practice is the balanced group accuracy. Okay, so you're going to minimize the accuracy for all the groups, and everybody will get the same accuracy. All right, so I'm going to put down some theorems that I have in this setting. Again, I look at squared loss. It's easy to analyze. And then we assume that the data set has these, each one of these groups is Gaussian. Okay, so we have structured Gaussian data assumptions. What I can show is, even in the population setting, upweighting or downsampling has better performance almost all the time compared to ERM. The only time the performance is equal is when you already have balanced groups. So you should be upweighting or downsampling. It's actually better for you. And what do I mean by worst group accuracy? This is the smallest accuracy you get across all the groups. And we're going to replace, and worst group accuracy is optimized by optimizing balanced accuracy. Okay. All right. So what do we mean by this? So let's visualize the cancer data set as follows. All right. So blue is the data set that comes out of one hospital. Blue is the data set that comes out of cancer, and red is, well, let's make red cancer, and blue is the no cancer. Both data sets have data from two hospitals. Those are indicated by the square and the triangles. Okay, so in the rich hospital, this is all coming from. So this, remember, this is no cancer. For the rich hospital, this is going to be the most of the data. For the poor hospital, this is going to be most of the data, but some of them will also have no cancer. So what I'm trying to say here is that within each class, there are two groups, and those are coming from the two hospitals. Okay. And each of the hospitals is using a different stain. So these are two different stain colors. Okay, so when you do ERM favors the majority groups, and it sort of places little importance on the minorities. So what it'll do is it'll diagnose cancer better in one of the hospitals and diagnose no cancer better for the other hospitals, because that's where the majority of the data is coming from. Whereas it'll miss cancer and no cancer in some of these groups. Okay, so ERM by itself is going to weight the majorities more than the minorities. Okay, keep in mind this domain data sort of comes in along the way. Okay, you're not explicitly optimized. I mean, classification is all about just the class, but the domain, you have access to this domain annotation. Okay, so this is what happens, and what upweighting and downsampling do are as follows. Upweighting and downsampling basically allow you to upweight and downsample all these groups instead of just the classes like we did before. And then you get a different line that may take a little hit on the majorities, but allows you to do well on the minorities. And now majority and minority are with respect to a group. So this is cancer, one of the hospitals, no cancer, cancer, other hospital. No cancer, one of the hospitals, no cancer, other hospital. Okay, because these two hospitals are in different locations, the groups that have cancer and no cancer are different. And so you end up not doing well on some groups or the other, and you don't want false negatives, and you don't want false positives, or you don't want misdetection. And this is why you want to do well across all the groups at both hospitals.
Sorry, Lalitha, can I ask you
Yeah.
a question super quickly? I got a bit confused in the picture. Is zero is like red no cancer, blue cancer, and ST the different hospitals?
Yes. So
Okay.
red and blue are the two classes, and S and T are the two hospitals.
Okay, cool. So right here,
So
ERM was kind of, yeah, I see. Makes sense.
exactly. So what's
Yeah.
happening is so if you're near a Superfund site, most of your data here is going to come from the Superfund. Of course, it'll also come from the other hospital, but you have fewer samples from the rich hospital for this cancer. And this is not good, because what is going to happen is that the model will learn, the model actually learns that the stain, remember, hospital is equal to stain color. So purple stain means cancer, pink stain means no cancer. And that's what happens. People have observed this in practice, that these models learn spurious correlations. And you can explicitly classify these spurious correlations through these groups. And that's what I'm doing here. So now I want to give you group level accuracy instead of class level accuracy. Okay. All right. So, and you can do that by using the same worst group. I see a question in the chat box. I'm going to let you ask me that. Okay.
It's a comment, not a question.
Okay. What is the comment? They can't see something?
It's not important. Don't worry.
It's mostly a joke.
Oh, okay. Okay. Oops. Jokes are good. I want to hear it. Okay. Maybe at the end. So this is, in theory, at the population setting, I can show you that upweighting and downsampling are doing really well. Okay. So, but in reality, you can get this hospital 1, hospital 2, or the stain color annotation in your data, and then you'll do really well. You can use it. That's the only way you can get this worst group accuracy. But oftentimes, you may not have the annotations precisely. Okay, so now I'm not talking about class label errors. I'm talking about domain. So class is cancer, no cancer. Domain is hospital A, hospital B. People can make mistakes in notating hospitals. People do it all the time. All right. Domain noise is common in many data sets. What have I talked about so far? I have told you, hey, when you have so much imbalance across your groups, you can upweight the minority groups or downsample the majority groups to do things, and you will do better. However, if your labels are wrong for your domains, like hospital A, hospital B labels are wrong, you won't do well, because the majorities will have most of the errors, and your data set is going to look balanced across the groups. If you randomly pick something to make an error, because people annotate not on purpose, but they randomly make errors, you will actually end up with a more balanced group data set than actually is the case. So you can't use the method I just suggested, use the domain label, upweight it, or downsample it. It won't work. You need to augment your data in a way that is agnostic to the domain labels. Okay? So here's what I'm going to first tell you. How does domain label affect accuracy? So we're still in the squared loss setting. We're still in the last layer retraining. So it's a linear model. We assume that these hospital A, hospital B groups are uniformly at random, flipped with this noise probability P, a Bernoulli probability P, it's less than half. What happens then is that the performance of upweighting and downsampling actually strictly decrease. And they get closer and closer to that of empirical risk minimization. I call it SRM, statistical risk minimization, here because this is all in the population setting. I can only prove theorems when I assume I have expectations. My first result was in the empirical setting. I can do the same here, but I did it in the population setting. So what this tells you is that you can still upweight and downsample, but if you have a lot of noisy labels, it's not going to do well. So what is our solution? Our solution is pretty rad, and it's actually what's called regularized annotation of domains. So what we're going to do is we're going to implicitly annotate. We're going to throw out the domain labels, not use it because we don't trust it. And we're going to implicitly annotate the domains so we can still do it. So one of the key ideas of all of this is, remember, we started with a deep model, maybe a foundation model, a deep model, and we're looking at the last output before the linear layer of this model. We all know very well that deep models learn not just relevant features, they absolutely learn spurious correlations. Because this deep model it's driven to minimize the loss. And if it's minimizing the loss empirically, it's going to look at, hey, most of the data is here, most of the data is here. This is a light pink color, this was dark pink color image samples. I'm going to learn that. That's a spurious feature it is learning. What people have been doing in practice to eliminate spurious features is to add a strong L1 penalty as a regularizer when we do last layer retraining. Okay? And then you also create a balanced data set either by upweighting or downsampling. So a strong L1 penalty on a balanced set leads you to learn relevant features and throw out spurious features. But now I don't have a balanced set because my domain labels are noisy. So you know what I'm going to do? I am going to take the imbalanced data set that I have, keep it as it is, keep a very strong L1 penalty. Okay? And when I do that, I'm going to learn the fewest number of features, typically either the core features for cancer, like the cell size, and this hospital stain color. All right? And this model will not perform well on the minorities at all because it is so limited in the features that it is using. And it'll absolutely include the spurious features if spurious features are important. If spurious features are not important, then it's okay. Then there's no problem. We can just, you'll get errors on a lot of them and you can solve this. But if spurious features are important, then you'll sort of learn these two classes really well because of their colors, but you won't groups really well and you won't learn these groups. And keep in mind, now you have errors, you've thrown out domain labels, and this is what you're doing. You're using this very strong L1 penalty on the original imbalanced data set you have. And the misclassifications are likely the ones where you don't do well. You're going to call that your minority set and learn on that. So let me tell you what the RAD algorithm is. It uses a biased classifier to pseudo-annotate the examples. And then it upweights the pseudo-annotated examples. And it trains a fair classifier using this augmented data set. So I'm not using the original group, this domain label at all. I'm not using hospital A, hospital B, because I know there are lots of errors in this. Somebody did data entry errors. What I'm doing is I have all these last layer representations. I'm going to run it through a linear model, but I'm going to put a very high penalty on my L1 regularizer. With very high likelihood, it's only going to learn the best samples to classify and the spurious correlation. And then I take all of those samples which were not learned well, and upweight them. They are the error set. So here is our algorithm. First, you take your whole data set, it's naturally imbalanced. You train this L1 constrained classifier, you take your error set, you upweight it, you keep your not errored set, you're obviously weighting that by 1, and now you train a fair classifier. So what RAD does is uses a strong L1 penalty to learn a bias classifier and upweights the error set. By the way, Vidya Muthukumar and her student Tyler LeBond had a prior work on this where they did it slightly differently, and they never used these samples at all. And we ended up doing better than them in a variety of settings, but certainly their work was very cutting edge when it was done. It was the state of the art. So I wanted to throw out a shout out to that team. Okay, so experimental results. I'm going to talk about 3 data sets here. These 3 data sets are actually very well-known spuriously correlated data sets. So the first one is the MNIST data set, where I color the first 5 digits with one color and the second 5 digits with one color. And you're doing binary classification, first 5 digits or the last 5 digits. And what happens is color becomes spuriously correlated. And when you bring in a new data set with a different imbalance or with a different color scheme, they do not do well. All right. So, and CELEB A is about hair color. There's a natural imbalance in the data set. There are far more blondes because it's celebrity than non-blondes. It doesn't do well on non-blondes. And you want this to work well in the field across all kinds of imbalances. And gender is the spurious correlation here because more women are blonde than men. Okay. So male blondes are the smallest group here, and we want to make sure they get fair accuracies. And similarly for water birds. And in all of these, what am I showing you? Let's just look at the center plot. If you have increasing domain label noise, the well-known methods of upweighting and downsampling that I spoke about before start performing really badly. They drop by almost 10 to 15% in accuracy. Whereas RAD consistently performs well because it doesn't use the domain labels. Okay. On the other hand, it takes a hit in performance at the beginning because it's not using clean domain labels. So depending on whether you want, if your data is noisy or not, you can be in either one of these settings. And you see this performance consistently across all the groups, all kinds of data sets. Okay. All right. Now, in the last part of the talk, what I'm going to tell you is, what if you had class noise? This is terrible, but radiologists look at the image and they put out something and they say cancer or no cancer, but there could be an annotation error. There could be a typing error. There could be all kinds of things, right? And so then your data is going to go from here to here. All the groups, no cancer, cancer, irrespective of the group, hospital A, hospital B, you can have these errors. So now you don't even have good class labels to fine tune on. How do you do things? Seems like a crazy problem, right? And what happens if I use this RAD algorithm that I already had, because my class labels are also wrong, I would include a lot of them unnecessarily in the error set. If these labels were all correct, now these are cancer data and they're going to be called no cancer. This is no cancer, it's going to be called cancer. That's terrible. And they're all going to be included in the error set, and that's just not going to help the classifier. So how do we still learn a fair classifier, which does, by fairness, across all the groups? Sorry, my mouse is moving fast. In spite of the noise. Any guesses? Okay, so what I'm showing on this plot here is how a 2-dimensional representation, and this is just a t-SNE representation, of the latent, the last layer features for these different data sets look like across the 2 classes. What should immediately catch your eye? Yes, there's an imbalance in the data, but that blue groups look clustered. Blue is blue is blonde, non-blonde, 0 to 5, 0 to 4, 5 to 9, water birds, birds on land, birds on water. Okay, these things, they are clustering by themselves. Keep in mind, the labels are wrong. The representations are not. And it's actually been very well studied and shown that most deep models learn good representations of the data, even if the domain labels are wrong, because the domain labels largely come in when you do the last layer classification and score matching, score learning, and so on. Okay, so one thing we can do is we don't trust our class labels, we can correct our class labels. All right, so what we can do is in the ambient space, you're not going to see this, but in the latent space, you see these kinds of semantics and clustering. Okay, so what can we do? We can do KNN. We can actually clean the labels by label spreading. So you can use these either one neighbor or two neighbors or more than those neighbors. And this is what I'm showing you. If you use more and more neighbors, you actually do really well on the clean accuracies. Okay, for all of these data sets. And that's what we do. So now our algorithm looks like this. You don't trust your domain labels. You don't trust your class labels. You're first going to clean for the class labels by finding the k nearest neighbors. You set your label to the majority. Yes, you might make some mistakes on the boundary between the two classes, but otherwise you're going to have a very large group. That's clean, especially in the latent space. And then you have a clean data set. Now you can run RAD because you don't trust the domain labels. So you've added another pre-processing. Okay. All right. So let's just look at one of the data sets, CELAB data set. And here's what it looks like. Now I'm looking at a function of label noise on the x-axis. RAD by itself really does so badly as the label noise goes above, there's like a phase transition from 10 to 20%. Okay, it's really bad. So when I clean for it, so I can do KNN RAD or KNN self. Self, by the way, is Muthukumar and Labonte's work, where they do it slightly differently. They have domain noise and they fix it. Now we're combining it with KNN. And both our methods do well. KNN RAD is slightly better, but these are very good methods relative to not doing anything, relative to just using the noisy class labels. Okay, so this is sort of where I'm done with my presentation. Very briefly, can these kinds of, when you know that the label noise, when you know there's imbalance, forget noise, when there's imbalance in your data, can you do well in very large models, such as foundation models? And we know that fine-tuning foundation models, you can't just do last layer. There's no notion of that. You have to do really any intermediate layer. You fine-tune a very small fraction. And so those are things that will fall in test time training. You're fine-tuning a very small number of entries, parameters, and training at test time with a very small number of samples. So again, you want to be not in the over-parameterized regime, but in the proportionally parameterized regime. So you can't fine-tune too much if you don't have too many samples to train at test time. Yet another approach is what's called in-context learning, where you can't train at all. You provided context and the model is going to learn. Okay, there's no training. In all these contexts, in both of these settings, your data will naturally have some biases and imbalances. Can you still address these imbalances in new ways? This is what we're working on. We're looking at prior trained networks and using it for LLMs. This is all just really very beginning stages. I don't want to talk much about this. We're also looking at using these kinds of weightings to do mixture of experts routing. One thing we've done recently that may be of interest to people here is we've also looked at diffusion models and observed that when you train diffusion models on imbalanced data sets where there's a class associated with these images, diffusion models do really well on the head classes, the majority classes, and terribly on the tail classes, the minority classes. And the reason for this is in the latent space of the UNet, the tail classes do not learn good representations and they spread or they entangle over the majority classes. And this is why you get terrible fidelity and diversity of those samples. And what we've been able to do is say, observe this entanglement in the first place, and then disentangle using contrastive losses. And we're now extending that to multimodal generative models. So here are all the papers if anybody is interested, and I am going to stop here. Hopefully that was on time.
Yep, you are perfectly on time. So thank you once again for the great talk. And now it's time to take questions. Oh, actually, that was my question. Can you go back to this slide? I just need to take a picture.
This one?
Yes, thank you.
Sure.
If anyone else has a question, please go ahead.
Thank you, Leo. Yeah, I would love to answer any kind of basic question if there's something you missed anywhere. Like, what's the difference between class imbalance and group imbalance? This is a small group setting. Most of you are probably young researchers. So just feel free to ask any kind of question. There's no wrong question. No worries. Oh, okay.
All right. I mean, I guess we don't have any questions right now. I can just stop the recording and thank you again for the talk, Lalita. That was amazing. Thank you.
Okay. Thank you for attending, Leo. Feeling increasingly bad how I live next to a super fun site. That's too funny. I know. Thank you, Ira. We don't know.